Welcome back. We are in week 4 for inverse methods in heat transfer. In the previous video, we saw that when you try to apply gradient descent to nonlinear regression, at least the problem that we looked at, so this is somewhat difficult to make it converge. So we got some answers and those were far away from physical answers, etc. There are other problems that tend to happen in gradient descent, which I'll discuss more when we come to week 9 or so within this course. But gradient descent is not ideal for the simple inverse problems that we tend to do in heat transfer. It's actually better provided you can play a little bit with it for actually, ironically, more difficult nonlinear problems, because it's harder to do some of the techniques that we are going to use in such problems. Okay, gradient descent is the only one that scales in that case. So we are going to define something that works. What works for nonlinear regression? So remember, we are trying to simply minimize a function, a squared function of the loss. So we are trying to find out what works for nonlinear regression, especially in somewhat simple cases. So there are a couple of algorithms that work here, and we are going to look at one. One is called the conjugate gradient method. Most probably, we won't have the time to cover that within our course. So that's a popular way too. But we are going to look at what is known as the Gauss-Newton algorithm. But before going to Gauss-Newton algorithm, so before going to GNA, as we call it, we are going to have a few steps. Really speaking, the origin of GNA, the way I'm going to derive it, is from two places. One is the normal equations for linear systems. This was powerful, as you remember. And the other technique is what is known as the Newton-Raphson or the Newton set of equations for nonlinear systems. Now, nonlinear systems are just an extension of linear systems of equations. So please remember the difference between linear systems versus nonlinear systems. So linear systems are like this, or also remember this difference between linear systems versus linear regression. So linear systems are something like you have a matrix and you have x1, x2 up till xn, and you have some right-hand side. Let's call it b1, b2 up till bn. Okay, so this is a linear system. A non-linear system is something like you could have a11 x1 square plus a12 x2 plus a13 x1 x2. So these are the variables we are solving, please remember, and these are the parameters that we are solving for. In such a case, this is of course non-linear in x1 x2. Some of you might be more comfortable now if I call this a11 w1 square and a12 w2, etc. Okay, so in such a case, it's non-linear in w. So this is a nonlinear system. But look at a third case, which we have already solved, which is linear regression. Linear regression was the problem that we had these data points and none of them actually were on a line, but we fit a best fit line. But there's another way to see this linear regression system. It's like this. So suppose the line we are trying to fit is W0 plus W1x. And again, right now I am using W0 and W1 as the unknowns. So one way to say it is, if this point is the point x1, y1, and this is the point x2, y2, we are trying to solve two incompatible equations. So for example, I am trying to say that W0 plus W1 x1 should be y1. At the same time, W0 plus W1 x2 should be y2. You could solve these two, but I have a third point, which is x3, y3, and I'm trying to solve W0 plus W1 x3 equal to y3. These seem like mutually incompatible conditions. Now, there's a beautiful argument through linear algebra where you can show that you can think of this as solving an overdetermined system. Okay, so here you have only two unknowns, W0 and W1, and then you have one x1, one x2, up till one xm. Okay, you have only two variables, so n equal to 2, but you have m equations, and m is much greater than n. Now, all these we are trying to match to y1, y2, ym. Note that this multiplication is a valid multiplication because this is m cross 2, this is 2 cross 1, and this is m cross 1. So this multiplication is valid. Now, if you look at it, this will start looking like a set of equations x, w equal to y. Okay. This is what we want to solve, but obviously this is unsolvable as a system, but this is solvable as a regression problem. As in, you do not solve any of these equations exactly, but you solve them in an approximate sense. Now, some of you might notice that, strangely enough, it looks like our normal equations have something very close to this. If you look at the normal equations for this are x transpose xw equal to x transpose y. This is actually the solution to this regression problem. It's not a solution to the original problem because that problem is unsolvable. There is no line which will go through all these points. But the best fit line looks remarkably like this equation, except with an x transpose multiplied upfront. Okay, so something like this will happen when we come to nonlinear regression also. So first what we will do is we will gain intuition for nonlinear regression by solving the nonlinear system problem, which is a well-defined problem. That is, the number of equations equals the number of unknowns. And then we come to the nonlinear regression problem. What would the nonlinear regression problem look like? Physically, it will look like this. Okay, you're trying to fit a best fit line, which is very curvy, and it is not just a polynomial. It is actually nonlinear within the parameters itself. So we will find out that that algorithm is called the Gauss-Newton algorithm. Within this video, we will simply look at a nonlinear system of equations where the number of unknowns is equal to the number of variables, solve that, and then we will extend that to a nonlinear regression problem in the next video. So let's look at the first simplest case, which is the scalar nonlinear equation. What is a scalar nonlinear equation? It means x, the unknown is just one single variable. It's a real number. And we have an equation like f of x equal to 0, where f is a nonlinear function of x. If it was linear, it is straightforward. So for example, if f of x was linear, it would look like ax plus b equal to 0. Then of course we can directly solve this as x equal to minus b by a. Now this trivial thing I am pointing out for a specific reason. Notice how our knowledge of this linear solution will now be used to solve this nonlinear equation using the Newton-Raphson method. Now, all of you would be familiar with the Newton-Raphson method. Nonetheless, I hope I am going to give you at least a slightly new perspective on this. Look at it as a way to solve a nonlinear equation using our knowledge of how we solve linear equations. Okay, so we want to solve, so let's take an example. Let's say we have an equation something like x square equal to sine x. Then I will write it on one side. I will write this as x square minus sine x equal to 0. And this then becomes f of x. Okay, it's clearly a nonlinear function of x. Okay, how do we solve it? We know that we take a guess. Okay, so please notice this within the next three algorithms, we point out this step will always be the case. So we take a guess, let's say x0 equal to some value 3. Okay. Now, obviously, at x equal to 3 does not satisfy This should remind you of how we were searching for our parameters of gradient descent also. It does not satisfy x square minus sine x equal to 0. Okay. In fact, you will get x square minus sine x equal to some r, where r is something we will call a residual. That is, this remains for our guess. Okay. Now, how do we proceed? This is where we use Taylor series. You can interpret what we are doing geometrically. All of you would have seen this. I'm going to purely use Taylor series because that's what lets you extend this to nonlinear systems as well as to nonlinear regression. So Taylor series says, okay, let the new x be the current x plus some delta x. Okay. So notice this. We have a nonlinear equation in x. Notice what will happen to what the equation becomes in delta x. Okay. So let this new x be, if you wish, you can call this xi plus 1 is xi plus delta x I. But I am generally going to use the computer science notation or the programming notation that x plus delta x goes to x. Should be understood that this is the next iteration. This is the previous iteration. Okay. Now, what I want is that even though at x at I it's not 0, I would like that f of xi plus delta xi should be 0. Okay, now we expand this equation in Taylor series and say this means that f of x plus the first term of the Taylor series delta x times df dx at xi is 0. Now it won't be exactly 0 because we have ignored terms. So obviously this equation is not exact. It's approximate, but it is good for iterations. Okay, so many people confuse this idea saying that then the next step I should get an answer. Obviously I won't. All it is good for is for iterations. Now notice what has happened magically is this original equation, which was non-linear in x, is linear in delta x. Okay. So the original equation was non-linear in the parameters we are solving for. The new modified equation, which I am going to call the linearized equation, is linear in delta x. This is actually a fundamental insight in a lot of science and engineering. If you have a nonlinear curve is sort of like repeated linear curves. So if I really zoom in, it starts looking linear. So you can put together a bunch of linear segments and it will start looking nonlinear when you zoom out, okay, as you should be able to see. Okay, so similarly, what was nonlinear in x becomes linear when you put together many small delta x's. So you take small steps and the overall result becomes nonlinear. So this is simple. We already know how to solve this equation. And like I said, this is trivial. So you can now say delta x is minus of f of xi by f prime xi. So overall, you can write the algorithm, the Newton-Raphson iteration is x at I plus 1 equal to x at I minus f of xi by f prime xi. An easy way for you to remember which comes above and which comes below is dimensional analysis. F has the dimensions of f prime has the dimensions of f divided by delta x. So you need x, delta x, and x here. So this is the Newton-Raphson step. This is trivial. All of you would have seen it. We even have a question or two within the assignment just to refresh your memory. But you will see that slowly we will add complexity to it. So as long as you understand whatever I talked about so far, it should be easy for you to go further and actually go to the nonlinear regression case. So let's quickly see an example of this. So let's say I want find the cube root of 10. So this means solve x cube equal to 10, which means solve x cube minus 10 equal to 0. So this is our f of x. So our iteration is going to be x I plus 1 equal to xi minus f of x divided by f prime x, and f prime x here, of course, is 3x squared. So we can repeat it from some initial guess. Again, like I said in the previous videos, in case you are doing this for credit, please do get used to doing these things by hand. Let's look at a quick code to calculate this from a few initial guesses, just to see how Newton-Raphson moves, and then we will actually move to the nonlinear systems case. So let's go to the code now. So here is a very simple code for Newton-Raphson. You can see that I have defined the function x cube minus 10. I have also defined the gradient of the function, or the derivative of the function, which is 3x squared. And I have taken some random initial guess. I am running it for 10 iterations. This is not the best way to do it, but we could just look at what happens with, let's say, 5 iterations. Quickly, we can also check what the actual cube root of. So I think I made a mistake. So what is the actual cube root of 10? So you can see this number, okay, 2.1544, etc., ending in 884. Now let's actually try the Newton-Raphson method. Okay, so I'll put a breakpoint here and run it. So the current value of x is 3. Now you can now check. X very rapidly has become 2.37 from 3. We could also start with a far off guess. It would still converge in this case. Okay. So now you see it has now updated it to 2.17. Now, if I continue, and you can see it has actually converged to the final value in about 5 steps. Once again, you can actually check the cube root of 10. Non-different, so it has actually converged to 16 digits of accuracy just within 5 steps. This is one of the magic of Newton-Raphson. When it converges, especially when it's near the root, it has what is known as quadratic convergence, and it can converge really, really fast. Okay, so for all practical purposes, it will converge to the right answer really, really rapidly. Okay, so there is some difference between here and here, so we can actually run for a few more iterations and see how well Newton-Raphson does. So now you can see from here, there is some improvement, and I can also check the actual cube root. Okay, so now this is non-different from before. So this is the advantage of Newton-Raphson. As we proceed, we will now see how to extend the same idea to a system of equations. So let's now do that. So we can now look at Newton-Raphson or Newton algorithm for a system of equations. So let's say we have 2 equations in 2 unknowns. So let's take an example. An example makes things much easier. So example, let's say we have this equation x1 square plus x2 square equal to 4. And we also want, this is 2 variables, so we also want, let's say, x1 plus x2 equal to 2. So all of you can quickly imagine what this would look like on the plane. So something like this. The first one is corresponds to a circle of radius 2. The second equation is a line. So it would be something like this. And you can see that these two intersect at 2 points. So this has 2 solutions. So 2 equations, 2 variables. Because of the quadratic and because it's nonlinear, it actually has 2 solutions. So Newton method, as I will show you, depends on where it converges, depends on where you start. Okay. So this could have been also a problem with gradient descent and might be one of the reasons why it converged to a unphysical answer. But more importantly, for our case, gradient descent took too many iterations. So what we are trying to get rid of within the nonlinear regression case is to get rid of the too many iterations problem. So let's say we now reformulate this again as two equations of the form x1 square plus x2 square minus 4 equal to 0. And similarly, x1 plus x2 minus 2 equal to 0. So now we have two equations. So I will call this f of x1, x2 is 0. We can call this g of x1, x2 equal to 0. Another option is to call this f1 of x1, x2 equal to 0 and call this f2 of x1, x2 equal to 0. So let's make this choice. Okay, f and g if required, but I'll typically use f1 and f2. Now put together, we can now see this as a case where I'm saying f, capital F of x1, x2 is 0, where f is now a vector, which is f1 of x1, x2 and f2 of x1, x2. So which is, of course, in this case, x1 square plus x2 square minus 4 and x1 plus x2 minus 2. We want to solve f for some x. Capital X is again x1, x2 equal to 0, and this 0 on in turn is actually 0, 0. So this is now the nonlinear system. Now, once again, we use the same idea as before. See, this is nonlinear in X, but maybe we can linearize it so that it is somewhat linear in delta X, or it is linearizable in delta X, and we ignore the higher order terms. And we know how to solve a linear system of equations. So we do the same thing that we did for one equation. We know how to solve a linear equation in one variable. We use that to solve a nonlinear equation in one variable. Similarly, we know how to solve a linear equation in many variables. We use that to solve nonlinear equations in many variables. It's the same idea again and again. We'll do the same thing with regression. We know how to solve a regression problem, a linear regression problem. So we will use that to solve a nonlinear regression problem. The same trick we apply multiple times. Okay, so let's come to this. So let's say we take a guess for x. So let's choose some guess, something like 0.3, 0.7. We will know immediately that does not satisfy either f1 equal to 0 or f2 equal to 0. You can plug this in and check very quickly that this does not satisfy either of these cases. So now what do we have to do? Once again, we will postulate that there is a delta X, which corresponds to some delta X1 and delta X2. And the new X, okay, is going to be the old X plus this delta X. Okay. All right. We have the same problem as before. Now we want f at x plus delta x. Another way of saying it is, what is f1 at x1 plus delta x1, comma x2 plus delta x2, and what is f2 of x1 plus delta x1, comma x2 plus delta x2. It is for this precise reason that we had worked out the Taylor series for these two. Okay, so let's take this. So f1 at this new position, x1 plus delta x1, comma x2 plus delta x2, is going to be f1 at the old place, x1, x2, plus delta x1 del f1 del x1, Okay, how much ever f1 changes just because x1 has changed. Similarly, delta x2 times how much ever this function changes with x2. Okay. So this tells us that this is going to be, we want this to be driven to 0. This is what we want. Okay. So this tells us f1. I am going to leave it as f1. It is understood that this is being calculated at x1, x2 plus delta x1 del f1 del x1 plus delta x2 del f2, so del f1 del x2. Similarly, you can see quite easily the same trick applies for f2. f2 of x1 plus delta x1 comma x2 plus delta x2 will have to be driven to 0. This will give us f2 plus delta x1. If we perturb x1, f2 will change by a little bit. Similarly, if we perturb x2, f2 will change by a little bit. Now notice this. What are the unknowns in these two equations? The unknowns in these two equations are these terms. This is what we are trying to find out. Just like delta x was the unknown in the one variable case, delta x1 and delta x2 are the unknowns in the two variable case. What is known? We already know what the current value of f1 and f2 are. We also can calculate del f1, del x1, del f1, del x2, etc., etc. So let's rewrite this. Okay, so we can rewrite this as del f1 del x1 del f1 del x2 and del f2 del x1 del f2 del x2, the whole thing multiplied by delta x1 delta x2. Okay. So let's see what this corresponds to. I will write the equations and hopefully this will make things clear. This is equal to minus f1 minus f2. Okay. How did this come about? I moved this to the right hand side, to the left hand side, or flip this sign of the equation. So you get a minus f1 minus f2 here. In fact, we can now adjust this and call this minus of f1 f2. Okay. Now notice this multiplication, matrix multiplication. Here it comes to del f1 del x1 times delta x1, del f1 del x2 times delta x2, first equation. Second equation, delta x1 multiplied by del f2 del x1, delta x2 multiplied by del f2 del x2. Okay. Now notice the structure of this equation. This basically is our Jacobian. Again, this is not the loss function. This is Jacobian. This is Jacobian. Another way of saying it is this is the gradient of capital F with respect to x. I'm going to call this the Jacobian. I'll try to avoid confusion between the j of the Jacobian and j of the loss function. This, of course, is our delta x vector, and this is simply negative of our f vector. So let's see what the equation becomes. This becomes j times delta x equal to minus f, which means delta x is minus of j inverse f. Okay. So this is the Newton for a system of equations formula. How so? Very simple. Once you have a guess for x, now you write a linear equation for delta x. How much should I change x? And that equation becomes this. Now notice, j actually is a gradient. It is very much like gradient of f with x. Of course, we never really invert. We use, as I have said before, even with the normal equations, typically you'll use Gauss elimination or some other method to solve this. Most exam problems in this course will be something like 2 by 2 systems or something of that sort. So those you can solve by hand. It's usually making the Jacobians, which is a little bit harder. Or else for the assignments, you can use programs if you wish to. Now notice how symmetric this is to the scalar case. The scalar case was delta x equal to minus 1 by f prime times f. Okay. Notice this inverse. Another way of saying it is f prime power minus 1 times f. This is the same thing here. Okay, it is exactly the same relationship as before, except now J is a matrix. Here it was a f prime was a scalar. Of course, J is a matrix because it is now a system of equations. It is two f's and two x's. Okay, so once again, to summarize, the idea is initialize the guess for x, then update x as x minus Jacobian inverse of f. Of course, these two have to be calculated. And you repeat till convergence. That's it. This is Newton for a system of equations, and this is used in many practical places. Of course, it has trouble. In case J is not invertible, you will have trouble. Just like in case f prime goes to 0, you will have trouble. There are all sorts of convergence problems that occur for Newton also. Nonetheless, in practice, we will see next week, not this week, that you can combine this Newton approach with other approaches and make it better behave. So let me just show you a quick code for solving the system that I just popped up, just so that you have completion. And then in the next video, we will move on to nonlinear regression. So let me show you the code right now. Okay, so this is Newton for a system of equations. Hopefully, you are able to see it within your screens here. Maybe I can make it bigger just so that it's clearer. I have the same system of equations that I used in the theory just before. So f is made up of two parts, x1 square plus x2 square minus 4 and x1 plus x2 minus 2. And then we have the Jacobian, which we can actually calculate. Del f1 del x1 is just 2x1. Del f1 del x2 is actually, we should change this to 2x2. Yeah, I have written 2x2. So del f1 del x2 is 2x2. So that's correct. Similarly, del f2 del x1 is 1 and del f2 del x2 is also 1. So you have this Jacobian and you have the actual original function. So I give a random initial guess. Let's say I gave a guess that x equal to 0 0.1, 0 0.7. So let us go here and run. Now you can see that I'll take a quick step. You can see an updated x. So, but just to check what was the case, you can check what j of x is going to be in the next step. F of x is going to be in the next step. And you can also do something like inverse of j of x multiplied by f of x and solve this, but that's not very appropriate because for large systems, this is kind of inefficient as far as MATLAB is concerned. Okay, so, but you can now see that x has been updated. The new x now is from where it was, it has now become minus 1.41 and to 3.41. This might or might not be a good thing. Let us see whether this initial guess works for what we are trying. So I have given 10 iterations. Now you can see that after a few iterations, maybe after 6 or 7 iterations, it has now converged. It was already going to 0 and 2 very rapidly. If you remember the graph that I had shown, one of the points where we could get to was 0, 2. That was on the y-axis. Now, it is probably possible that if I change the order of the guesses and make this 0.7 and 0.1, it will actually converge to the other value. So let's check whether that's the case. Yeah, that's indeed the case. So the other solution now attracts it. because this point is farther along the x-axis and this point is closer to the origin in the y-axis, you actually converge to the other solution. So this is the power of a Newton iteration for systems. So just for a 2x2 system, we actually rapidly converged to the answers. And now our question is going to be, can we do the same thing for a system of equations, especially when in inverse problems of the sort that we have been considering so far? We have very, very few parameters in the nonlinear equations. When the parameters are large, gradient descent is better. But for a low number of parameters, it turns out that something like what we did for a system of equations here, if we could do it for regression, that would work well for a low number of parameters also. So we will both derive as well as see a solution with what is known as the Gauss-Newton algorithm in the next video. So I'll see you in the next video. Thank you.